are in Introduction to Statistical Learning, Chapter 9, and we're on question 3 here. Here's the questions, and so we'll go through them one at a time. But basically, we're looking at a small data set right here, where we have 7 observations that have two, call them coordinates or descriptor variables that we'll be able to plot very conveniently, x1 and x2, and and they also have a label called y here, and the label y is a color, red or blue. Okay, so that's called part A. That's part A. All right, and we are meant to sketch these observations. And so I've just converted the table that we're given into some R code here, and then I plot x2 against x1 and color them appropriately, and we get this right here. So you see some red dots and some blue dots, and you can see that the red dots are kind of on this top left part here, and the blue dots are in the bottom right part of the plot. Okay. So now in part B, so just eyeballing this, it looks then like we could kind of separate red and blue with a nice line right through the middle of some, of their territories. Okay, and that's what we're doing here. So we're going to sketch a separating hyperplane, but not any separating hyperplane, right? There's infinite lines that we could draw separating these two classes. We're looking for the optimal separating hyperplane, and then to provide the equation for it. Okay. So the first thing we need to do is to find. Let's just walk through the logic here. If I'm going to separate these two classes, red and blue, I really just need to find the points, the data points from the two classes that are closest to each other, right? Because that is the passage through which the hyperplane is going to have to thread itself. Okay, so if I'm just eyeballing these, so here's a pair right here, and here's a pair right here that look like they could be candidates for being the closest. Okay, but we don't have to consider this guy down here, because at least one or maybe both of these other vectors here, or I'm going to call them data points, are closer to the red than this guy is. And similarly, we don't have to consider this red guy up here, because one of its compatriots is much closer to the blue, right? So we just need to find the data points that are closest to the other class, and we call those support vectors. Okay, so why are they vectors? Well, because for any one of these data points, we could think about them as a vector, right? I mean, so one of these data points is 3, 4. 3, 4. That's that data point right there. And so we could call 3, 4 a vector coordinates, okay? And why are they support vectors? I guess because they are supporting, supporting the hyperplane that is going to optimally separate them. I guess that's maybe why we call it that. Okay, so all of that to say, we need to find the distance between each red point with each blue point, all right? And so we can easily do like Euclidean distance, which is given right here. Okay, so we take the x1 coordinate of the red minus the x2 or x1 coordinate of the blue, square that, and then same for the x2 coordinate, take the square root, and then that's our distance. Okay, and so what this code right here does is basically implement that over all of our data points. Okay, and so here we get a distance, or a matrix of all of the distances between all of the red and all of the blue points. Okay, and then this second one right here says which of these is equal to the minimum distance. Okay, and so you see that red 2, blue 1 is one of them, okay? Or stated differently, blue 1 sorry about that, I broke some code just a little bit ago. Let me redo that here. Okay, so here we go. Okay, so this top matrix gives the distance between each red and each blue dot. And then for each red dot, we get which blue dot is closest. Okay, I'm not entirely sure that this second matrix is necessary. But then we go through and we look for the distances that are closest between the red and the blue. Okay, and so we have two vectors here. So the second and third red and the first and second blue. Okay, as portrayed here. Okay, and so now the coordinates then for these different vectors are given right here. Okay, so that code is a little bit confusing, but the payoff, once you walk through all of it, is we can now run that code and get this pretty picture, which is exactly the same, but now the support vectors are highlighted by being enlarged. Okay. All right. So that's not the end of the task here. We need to find the optimal separating hyperplane here. Okay. So now our optimal separating hyperplane should be equidistant between the support vectors. Okay, or these companion support vectors, right? So it should thread the middle along here. So we need to find what the distance is, between this and this, which is going to be equal to the distance between the other pair. And so that happens to be 1, right? The minimum of the distances is 1. And so because the hyperplane needs to evenly split these, well then the hyperplane should be half, 1/2 unit between, or to either member of the pair. Okay, so we have that. All right, and so what we need now is to find the formula of a line that meets those requirements, right? That is half a unit away from both the red and the blue support vectors here. So what then are the coordinates of this line, right? Well, if we think about the blue points, right? So here's one of our support vectors right here, and it's at 2, 1, and we need to add 1/2 to that. So that would be that. Well, that is the same as taking its counterpart, 2, 2 in red, and subtracting half. Okay, so one of the points that our hyperplane needs to go through is 2 on the x1 axis and 1.5 on the x2 axis. Okay? And then we do something similar over here for the second pair of support vectors. Okay, well now we have 2 points, and with that we can find the slope, which is just rise over run. Okay, and so how much are we rising between between this point and this point? Well, we just subtract. We just find the difference in the vertical axes, or the x2 axes, divided by the difference in the horizontal running axes, the rise over the run, and then we get a slope of 1. Okay, and so now we need to find the intercept for our line, right? Because our line can take on this form here. Okay, and so how do we find that? Well, we just simply solve for the intercept from this equation right here, right? So we subtract alpha over, and then subtract y over, and so on. And then we plug in, we already know the slope, and then we plug in our values for, this is a little bit confusing, but for the y and the x, which is actually, the x1 and x2, okay? And so we have, so if this is what our formula starts by looking at, right? Or starts looking like. x2 equals the intercept plus beta 1 times x1, okay? If we subtract the x2 over, we know that beta 1 is 1, right? That's the slope that we already found, okay? And so, so our hyperplane fulfills this criteria right here, okay? So that is the formula for our hyperplane, okay? And so we can plot that, and so it's plotted right here, okay? And you see that we have this hyperplane that is separating the red and the blue classes, and it goes right down the middle, okay, just like we wanted. Okay, so what if we want to formulate this in terms of a rule, right? If I give you x1 and x2, you tell me whether it should be red or blue. Okay, so we want a rule, and that's what we're doing here in part C. And so you know, there's different ways to do this, but I'm just going to instantiate the rule on our existing data set here. Okay, and I'm just going to look for a pattern for whenever something is greater, you know, when our criteria for the hyperplane is not 0, and in fact it's greater than 0. Okay, and so what we see is that all of the reds are not greater than 0, and all of the blues are, right? And so we could instantiate this rule as you know, so take this arrow as the logical operator if, you know, if then. So if this is fulfilled, right, our point is above the hyperplane, greater than 0, then it's blue, else it's red. Okay, I shouldn't say above 0 because, you know, above makes you think that it should be up here. But, you know, what we really want is for this expression to be greater than 0. If that's the case, then it's blue, otherwise it's red. So, okay, and so so next we've sketched the hyperplane. Well, we also want to fill in the margins. Okay, so you know, the space between the hyperplane and the support vector. All right, and so we're gonna draw those for part D, and then also indicate which ones are support vectors. We've already been indicating which ones are our support vectors, but here it is. And so this is the same code for the above plot, but now we've just added some margins here, and we just simply did that by taking the hyperplane, the solid line, and then changing the intercept a little bit, right? So we had that the intercept was negative 0.5, so we add a half, subtract a half, okay? Again, why a half? Because we already know that the distance between the hyperplane and the support vector needs to be 1/2, right? So if we just kind of move that intercept up and down, we land on the support vectors, okay? All right, now in part 7, we're supposed to argue that if we were to move the 7th data point, which is located at 4,1, so it's this guy in the bottom right corner, that it wouldn't affect the maximal margin hyperplane, you know, the thing that we've already found. Okay, well, so the argument goes that like I was saying in the beginning, that this hyperplane only needs to consider the data points from either class that are closest to each other. And so long as we can move, you know, one of these non-support vectors, as long as it doesn't surpass the margin that has already been established, it is not going to affect, you know, what we have already done, what we've already found. So that's the argument. Okay, so now we're going to sketch another hyperplane that is not optimal, but is nevertheless separating. All right. Well, this is easy. You know, I mean, there's infinite such lines, and so in a way, it's easier to find one that isn't optimal. But you know, so here I've just adjusted the intercept, right? That's all I've done. and you could tweak the slopes and so on. But you notice now that the line here is not evenly spread, or evenly, or what I want to say, equidistant between the pairs of support vectors, right? And so it's not optimal, right? But again, there's infinite of these, and anybody could have very different answers. Okay, and finally, here in part H, we are going to draw an additional observation so that the two classes cannot be separated perfectly by a hyperplane. As we go on into as we develop these ideas, we will find ways of dealing with these imperfect data sets. But for right now, we're going to try to break what we've done here. We're going to try to break our ability to make the marginal or the maximal marginal hyperplane, separating hyperplane. And so I'm just adding an 8th data point, and it's right here. But now you notice that, okay, so that would fall strictly on the red side of the line. It's not shown in this plot. It's shown on this plot, but I didn't draw a hyperplane because we don't have a separating hyperplane anymore. But it would fall on the red side, and yet it is blue. Okay, and so with that, with that data point right there, we can no longer draw, a hyperplane that does not make mistakes, at least a linear hyperplane that doesn't make mistakes. So, okay, I think we will call that good.